To continue now, we have to Professor Anna Dubova introduce to Professor Maher Moakher. You can start, Professor Anna.
Okay, thank you very much, Juan. Thank you very much, Professor, for accepting the talk in our seminar. So, Professor Maher Moakher is a full professor in National of Engineering of Tunis. He is currently director of the Laboratory of Mathematical and Numerical Modeling in Engineering Sciences. His work are mainly related to Riemann means, image processes, matrix analysis, applied differential geometry, and computational mechanics. He has supervised around 16 PhD theses and 19 master's degree. He's a member of numerous research projects, and he took part of both scientific and organizing committee of several international conferences. So today he will give a talk entitled Geometries on the cone of positive definite matrices with application in science and engineering. So please, you can start.
Okay, thanks, Anna, and thanks, Juan, for this kind invitation. So today I will talk about geometries on the cone of positive definite matrices with application in science and engineering. So to introduce the talk, so at this information age, many application requires the processing of a huge amount of data, and some of this data are constrained to live on not linear space, but rather on Riemannian manifolds. For example, we have orientation data, orthogonal matrices data, and symmetric positive definite matrices data, etc. And we will focus in this talk on symmetric positive definite matrices, but the methodology that I introduce is rather general, and also I apply to orthogonal matrices and orthogonal orientation data. First, why we study symmetric positive definite matrices is because they are everywhere, they are omnipresent, and play important roles in many area of science. For example, in mathematics, they are can be found in matrix theory, in differential geometry. They are metric tensors, etc. They are positive definite matrices. In numerical analysis, when you discretize PDEs, for example, for the Laplacian or something like this, you get positive definite matrices. And you can use in numerical analysis Cholesky decomposition for such matrices, and also conjugate gradient algorithms for when you have quadratic function to minimize, and or not even a quadratic, but in conjugate gradient you need to deal with positive definite matrices. Also in cone programming, like interior point methods. In statistics, they are, for example, covariant matrices are positive definite matrices. And in physics, and many branches of physics like mechanics, electricity, etc., they appear as conductivity tensors, permeability tensor, elasticity tensor, etc. And more recently in medical imaging, where you have diffusion magnetic resonance imaging, which is a new modality for MRI. And also in computational geometry, to generate anisotropic mesh generation, you need to deal with positive definite matrices. So this is why we study the geometry of the set. And also another notion is the notion of mean. which is the heart of many data processing tasks, like they are used in k-means for clustering algorithms. And in the last few decades, there has been a growing interest in studying means on positive definite matrices. And this interest is motivated by theoretical, computational, and practical aspects. And there are some applications here, for example, smoothing, interpolation, classification of diffusion tensor MRI, effective computation of matrix means, and the theory of matrix means also from theoretical viewpoints. This notion of mean is very ancient, and for example, the Greeks defined 11 or 10 notion of means, which are based on geometric proportions. If you have three numbers, then you can construct, if you have three numbers or A, B, C, then based on the proportion between ratio of some of these, you can construct a mean. For example, you have two numbers A and B, A and C, then you can construct B by equating these proportions. And for example, the first three means here are the usual arithmetic mean, geometric mean, and the harmonic mean. And the fourth one is the mean root square mean. And there are other means, they qualify as mean, but some of them, they don't respect some properties of means. So these means have been generalized to more than positive numbers. For example, they can be generalized to positive functions, especially the three means like the arithmetic, geometric, and harmonic means. Then you can, if you have positive functions, then you can define these means. And in 1975, Anderson, Trapp, and Puss and Woronovich introduced a notion of, they call it the geometric mean of a pair of positive operators on a Hilbert space. And here are the several expression of the means, which is denoted if you have two positive definite operators A and B, then their geometric means is any of these equivalent expressions. This notion of mean has failed. There have been many attempts to generalize this notion of geometric mean to more than more than two operators, but most of the proposed definition failed because they don't satisfy many nice properties. But if we look at the harmonic, geometric, and arithmetic means, we can see that they all are minimizers of the square distance between the set of points to the mean. For example, if you take the Euclidean distance between two numbers x and y, which is the absolute value of x minus y, and you minimize the square distances, then you end up with the arithmetic mean. If you use a logarithmic scale, then this is the hyperbolic distance, because if you look at the hyperbolic geometry of the upper half space, then if the 2 points are on the same vertical, then it reduces to this mean, to this distance. And then if you try to minimize the square distances, then you end up with the geometric mean. And similarly for the harmonic mean. So this notion of means can be generalized then if you have a metric space. Then you can use this definition to generalize the notion of mean to more than two operators or two matrices, etc. For this, the outline of my talk is the following. I will first introduce the Riemannian geometry of the set of positive definite matrices. I will talk about a Riemannian metric called the affine invariant metric. And then also we can use Hessian structure on the set, and then we can define geodesics and distances. And then we base it on these distances, we can define means as minimizer of the sum of squared distances. Also, we will talk about information geometry of the space of positive definite matrices, which is based on a divergence function, which is the equivalent of a squared distance. So it satisfies the properties of a distance except perhaps the symmetry and the triangle inequality. And then I will give some application in science and engineering, and it depends on the times that I have. I will give several applications. Okay, so first, the geometry of the set of positive definite matrices is based on the Riemannian. We will introduce a Riemannian structure on the set of positive definite matrices. First of all, we have the set of symmetric matrices is Euclidean space, and the set of positive definite matrices is a subset of Sn for which A is positive definite. This is not a Euclidean space or a linear space, but it's the interior of a pointed convex cone. For a cone, if you take A and Pn, then if you multiply by any positive number, then you will end up with a point in a Pn. And convex, if you take a convex combination of two positive definite matrices, then also you have a convex positive definite matrix. And because this is an open set, its boundary corresponds to singular positive semi-definite matrices. And this set has been studied from several perspectives. For example, we can cite convex cones and the theory of convex cones in Riemannian manifold, Jordan algebra, information theory, etc. Okay, so to convince you that this is a cone, let's look at 2 by 2 positive definite matrices, which are matrices of the form A, B, and C, with A positive and AB minus C squared positive. If we make a change of variable, U equal 1/2 A plus B and V equal 1/2 A minus B, A minus B, then the condition A positive and AB minus C squared positive corresponds to C squared plus V squared is less than U squared, and U squared is positive, which is clearly the the equation for a forward light cone. Okay, so this set has a differentiable manifold structure, and it has a dimension of 1/2 n plus 1, and the tangent space at each point P of Pn is the set of symmetric matrices. And on the tangent space, we introduce an inner product to measure lengths and angles. And this inner product depends on the base point. It depends smoothly on the base point P, which is defined by the trace of P minus 1A, P minus 1B for every pair of AB that are in the tangent space. That means that they are symmetric matrices. And this Riemannian matrix defines the line elements can be, the square of the line element can be seen as the length of P minus 1/2 dP, P minus 1/2 squared. And this is, this metric is called the affine invariant metric, or also it's called the trace metric. Okay. What is nice about this metric is that it is invariant under congruent transformation. So if you have P and you pre-multiply it by a matrix and GLN and post multiplied by its transpose, then the length element stays the same. And more importantly, it is invariant under M inversion. The ds element of P minus 1 is equal to the ds squared of P. And this can be seen by this simple calculation. Okay, now once we have defined this invariant metric, we can look at the length of curves that are on Pn, and the length is given by the length functional, which is the distance of or it is the distance of the element ds squared, which is, as we have seen, is the metric of at P of P dot to the 1/2. And the extreme curves that are minimizers of this length are called geodesics. And if you write the Euler-Lagrange equation of this functional, then you end up with this Riccati differential equation, second order Riccati differential equation, and it is with some luck that we can write the geodesics explicitly. So the geodesics that emanate from P0 and the direction of a symmetric matrix S is given by this expression where, so it's P0 to the 1/2 exponential of T, P0 to the minus 1/2, S, P0 to the minus 1/2, P0 to the 1/2. And so if you derive it at T equals 0, you get S, and it starts at P0. This geodesic also can be used to find the distance between points A and B. So let's look at the geodesics in the Euclidean metric. Then the geodesic is equal 1 minus TA plus TB, and T it is not on the whole line, but it is at some point. For example, if you see here, the green line is the geodesic with the Euclidean metric, which starts at this point and this point. But this geodesic at some point will leave the set, the cone of positive definite matrices. On the other hand, if you look at if you use the Riemannian metric, and the Riemannian geodesic has this form, and it is defined for every T in R. It's for every value of T, it stays inside, which is this yellow curve that you see here. It is always inside the cone of positive definite matrices. And from the theorem of Hopf-Rino, it's if we can extend geodesic indefinitely, then we have a complete metric space. And if we use the usual Euclidean distance or metric, we will have not a complete space because, as I said, at some point the geodesic will leave the set of the cone of positive definite matrices. Now we talk about the distance between the 2 points, which is given by the geodesics that joins P1 and P2. And this, since we have the explicit expression for the geodesic, then we can get the explicit expression for the distance in the Riemannian sense between P1 and P2, which is the sum of the logarithm of the eigenvalues of P minus 1, P1 minus 1, P2. So we see if any one of the eigenvalues of P goes to 0 or goes to infinity, this distance will explode. And so this distance is, it will keep the point inside the cone of positive definite matrices. Also, we considered another or a generalization of this trace metric by considering a potential function, which is a strictly convex real valued function defined on Pn. And if we, since it is strictly convex, its Hessian defines a quadratic form, a positive definite quadratic form, and this quadratic form we use it as the Riemannian metric. So, for example, the metrics that we have seen is nothing but the Hessian of the logarithmic barrier function, which is minus log det of x. And this is people from information theory call it the information potential. From statistical mechanics, they call it the Boltzmann entropy, etc. And we generalized this potential function by introducing one parameter family of potential function defined by 1 minus determinant of x to the beta divided by beta, and this is strictly convex if this parameter is less than 1 over n. And as the parameter goes to 0, it will goes to the logarithmic barrier potential. So we just, because it is the limit, so we can just include this, and it depends if beta equals 0, it's the logarithmic potential, and if not, it's this, we call it the phi beta of x. And so these are the trace metric that we have seen is just a special case of the matrix that we will see now. Also, from statistical mechanics, they call it the Q logarithm or quantum logarithm is just 1 x to the 1 minus q minus 1 or 1 over minus q if q is different than 1, and log of x if q is 1. So it is the potential function that we introduced. It is just the 1 minus beta Tsallis logarithm or q logarithm. So it just has a nice interpretation. So since this potential is strictly convex, its Hessian define a positive definite quadratic form, and we can define a Riemannian metric. And this Riemannian metric now reads as it depends on beta. It's equal determinant of x to the beta trace of x minus 1 u x minus 1 v plus beta trace x minus 1 u trace x minus 1 v. So, and you see that when beta equals 0, it reduces to the trace metric or the affine invariant metric. It is not easy to find geodesics, but after long work, and we arrived to have an explicit form for the geodesic. And here the exponent, it's alpha of t, is has an expression which is not very compact, so I didn't include it here. And as we see, it has an exponential part, this part a minus 1b to the alpha t, but with the power alpha of t that depends, it not just t, and it has a scalar part eta, which is when we have two linearly independent positive definite matrices, then it corresponds to the 2 over n beta power means of A and B. When beta equals 0, as we expect, it goes to the geometric mean. And when A and B are linear and dependent, it's the n beta over 2 power mean. Okay, so using now these geometries, now we are going to define means on the set of positive definite matrices, as I pointed out in the beginning, is just by minimizing the squared distances, but also we can include weights. And this has led to the definition of the weighted arithmetic mean and weighted geometric mean. For the, if we use the Euclidean distance, then we have the Euclidean mean, which has this expression. But on the other hand, for the geometric mean, we don't have an explicit expression, but we need to solve this equation. And this equation means that on the tangent space at x, all the derivative, they sum up to 0. But if we have only 2, we can give the expression, the solution of this equation, if we have only 2. And these are the expression, which means that the weighted geometric mean with weight s and 1 minus s is nothing but the geodesics evaluated at s. Also, we have some nice properties. If we have several symmetric positive definite matrices and we scale them so that they have determinant 1, so P tilde k is equal to pk over the nth root of determinant of p, then the geometric mean of this pk are the geometric mean of the scaled matrices multiplied by the geometric mean of the nth root of the determinant of the matrices. And this is has a nice interpretation. If you want to take the average of several matrices, you can look at the surface of determinant 1 and you take the geometric mean, and also you take the geometric mean of their determinants and you get the answer. Also, if you have 2 matrices but in dimension 2, then we have a nice expression for the geometric mean. It has just we don't have exponential in this form, and this holds only for 2 matrices and in dimension 2, which is, and the proof is based on the Cayley-Hamilton theorem. Okay, now we go to the information geometry of the space of symmetric positive definite matrices, and first we need to define the notion of a divergence function, which was introduced in the 1930 to measure the discrimination between correlated normal multivariate distributions. And here is for the definition from Amari. A divergence function over a Riemannian manifold is a real valued function on the Cartesian product space, which satisfy these 2 properties. First, they are positive definite, and that means they are always positive and equal 0 only if x equal y. And it has differentiability properties. It is twice differentiable with respect to x, to the first variable, and it's Hessian with respect to the first variable when evaluated at y equal x is positive definite. So this is the definition that Amari generalized the notion of divergence that was introduced earlier on to Riemannian manifold. And the divergence function is, with these properties, is almost a distance function, except that it does not need to be symmetric with respect to its 2 arguments, nor to satisfy the triangle inequality. But in the in general, they are like the squared distances, as we will see. For example, if you take the square of a distance function is a symmetric divergence function. Here, how to construct a divergence function from strictly convex function is what is called the Bregman divergence is the Bregman divergence of with respect to f between x and y is equal f of x minus f of y minus the inner product of the gradient of f of y with x minus y. And this has an interpretation as this Bregman divergence is the first order approximation and the Taylor expansion of the function f around the point y evaluated at point x. And here are some examples. For example, if you take the function f of x equal 1/2 of x squared, then the Bregman divergence is just the square of the distance between x and y. And here, this function f of x, and these are 2 points p and q. And if you take the Taylor first order Taylor approximation of the function at p, this is the function, and then the difference between the function at q and this approximation is the divergence. There are other functions that are strictly convex. For example, x log x, and this will lead to the divergence function, Bregman divergence function, which is x log of x over y minus x plus y. Now, if we have another way to define divergence function from a strictly convex function is by using the definition. We have, in fact, a one parameter family of divergence, which are given by this expression, which is weighted with some parameter alpha. So it's 1 minus alpha over 2 f of x plus 1 plus alpha over 2 f of x minus the function evaluated at the weighted points. And what is nice about this, it is when the numbers, when alpha goes to plus or minus 1, it will go to the Bregman divergence. For example, when alpha goes to 1, we get the Bregman divergence of x and y. But when the alpha goes to minus 1, we go to the Bregman of y, x. And we know that the divergence needs not to be symmetric except in special cases. Okay, so now we can apply this definition of divergence function to the set of positive definite matrices, and we using the strictly convex Bregman logarithmic barrier function, and we can get these divergence functions. And when alpha goes to minus 1, we get what we call it the Kullback-Leibler divergence, and when alpha goes to 1, we get the Kullback-Leibler, but with reversed argument. And from we can have some nice invariance properties that if we take the divergence with respect, if we have congruent transformation, then it will have the same value of the divergence. And we have dual inversion. If we take the divergence with respect to alpha of a minus 1, b minus 1, it will be the divergence of minus alpha of a and b. And we have also the dual symmetry. If we change the order of a and b, then also we need to change alpha to minus alpha. And for example, there is one special case where you have invariance under inversion, and this is could happen only if alpha equal minus alpha, which is the zero divergence function. It is called the Bhattacharya divergence, and it has this nice expression. And it is the only alpha divergence that is symmetric and invariant under inversion. And it was proven by Sra that this is the square, this divergence is the square of a distance function. Since the divergence function is not symmetric, then we can define right means and left means by minimizing this function. Either we put the data point on the left or on the right. So if you minimize this with respect to the alpha divergence function, then we get the expression or the solution of this equation will be the right mean, and the solution of this one will be the left mean. And we, as we know that any mean should be between the harmonic mean and the arithmetic mean, and we proved that this alpha mean is between these two the upper and lower bounds, where the harmonic mean is this mean and the arithmetic mean is the usual mean. So, for example, if we have only two matrices, then we found this is nice expression. For alpha equal -1, it corresponds to the harmonic mean. For alpha equal 0, it corresponds to the geometric mean. For alpha equal 1, it corresponds to the arithmetic mean. And for alpha less than absolute value of alpha less than 1, then we have nice expression for the alpha mean. Okay, so we will apply the geometry, Riemannian and information geometry to some problems in science and engineering. And we start first with the interpolation of symmetric positive definite matrices. We recall that classical multivariate interpolation in n-simplex can be seen as a barycentric coordinate weighted arithmetic average. So if you have a function on a triangle and you have only the value at the summit of the triangle, then to define the value at the interior points, then you use the barycentric coordinate, and you have the first order approximation of the, or you can use a linear interpolation to get this expression with the weights are the barycentric coordinates. So in analogy with this, we define the interpolate to interpolate a field or a set of positive definite matrices. We use the notion of mean and barycentric coordinate. So for matrices that are defined at different points, then the solution will be we need to solve this equation. Here is an example of this interpolation. For example, let's say we have an hexagon and we only know the value of the positive definite tensors here represented by ellipsoids. So these ellipsoids are the semi-axis are the length of the semi-axis are the eigenvalues, and the axes are the eigenvectors. So they can nicely be represented by ellipsoids. So if we know the positive definite matrices at the vertices of the blue triangles, and we want to find the expression at the value of this, or to interpolate these tensors at the points of these red triangles, then using the Euclidean distance, we get this figure. And if we use the Riemannian distance and Riemannian means, then we get this one. And as you can see, for example, if you start from this tensor or positive definite matrix and this one, you see the one that interpolate in between, they have more volume than the original. But in the Riemannian, the volume is conserved. And this is a very nice property, because in data processing, this phenomena is called fattening, and which is an undesirable property. Another application is in diffusion-weighted magnetic resonance imaging, where the patient, for example, lies on this scanner, and they apply a slight magnetic field, and then they apply a gradient, and then they relax it, and they measure the displacement of water molecules that have been between the application of the gradient and when they relax it. As the human or live tissues contains a lot of maybe 70 to 80% of water. So we can measure the displacement of water molecule, and from this measurement we can infer the infrastructure of the tissue. So this techniques has been maybe introduced by Peter Basser in the 1990, and nowadays has become a routine clinical test in USA. And it is mainly used for the brain imaging and muscle and heart, because these are tissues that are not isotropic, and we can measure the anisotropy. For example, here for the brain, these are the encoding to find to extract the infrastructure. We need to infer the diffusivity and the direction. And since we have a tensor in 3D, it has a 3 independent component, so we need to estimate this coefficient, and usually they have 12 diffusion weighted directions and reference one, and from this they can estimate the diffusion tensor. Now, when they estimate this diffusion tensor, usually they have a lot of noise in the tensor field, so we need to regularize these tensor fields. And now, let's say, since this is a seminar on PDE, so I will talk about a little bit about PDE regularization of tensor valued images. Like the heat equation is well known to have regularization properties. So if we have a tensor, then we can apply the heat equation with C is the conductivity, and we start with an initial image which is usually noisy, and then when we apply the heat equation, it will remove the noise. But the problem is with this isotropic diffusion is that it will destroy it will remove the noise, but also destroy the important feature in the image. And there are a lot of work in this direction is to use the joint isotropic diffusion instead. So how to choose this conductivity is by this function. Also, there is an anisotropic version which is introduced by Weikert and Brooks. Now, we will apply this methodology to the Riemannian manifold in general. We have two Riemannian manifolds, M with metric G and N with metric H. And we call the first one the domain manifold, and the second one we call it the target manifold. And we construct a map which sends point on M to point on N. For example, in the diffusion tensor magnetic resonance imaging context, we can take M to be a domain in R3 with the Euclidean distance, and in the target manifold, is the set of diffusion tensors, which are positive definite matrices of dimension 3 with its Riemannian metric. And then we construct this map, and we associate to this map harmonic energy or Dirichlet energy. And when we minimize this energy, for example, with gradient descent, and it can be generalized or approximated to the heat equation or geometric heat equation, because here we have a Riemannian manifold. This matrix will introduce the Christoffel symbols. So we have, like the heat equation, it's a derivative with respect to T equal Laplacian, but we have here nonlinear terms first order, which are coupled with the Christoffel symbols. For if you have a Euclidean space, then all the Christoffel symbols are 0, and you get the heat equation. Otherwise, when you have a Riemannian manifold, then this will include the Riemannian structure. And also because this coupling, we can couple the denoising between the channels. And this is a very important property, because if you denoise each channel independently, then the edges may not coincide. And here we have a synthetic data of tensors, and we added some noise, and we tried to reconstruct by applying this geometric heat equation. But after a while, we have the contours are destroyed. So this led us to use energy functional that is not isotropic, like it is done in usual image processing. And for example, we have this function lambda squared log of 1 plus s squared lambda squared over 2. So this is a function which is like in the Perron-Malik, and this will lead to a more complicated parabolic equation, but it will has the desired property that if you have edges, it will stop diffusion. And here what we get, we have after we applied the heat equation, we still have see the limits between the two zones. And here another application is to use diffusion tensor images as immersion, and we take the domain manifold to be M, which is a part of R3, and the feature space we use omega tensor P3. And this has like a nice feature because we can use the Riemannian metric on both by a process called pullback. And this is the new geometry or metric which relates the G to the H of the Riemannian space N. And so if you use this the trace metric, then this new metric is the following. And we minimize the minimum energy, minimum surface energy. It's like the determinant is the surface area, and we get this parabolic equation with Christoffel symbols, etc. And this is the equivalent of the mean curvature flow because this is like the minimum surface energy. And here is what we get with more contours, and we after a while we recovered the initial data with before adding noise, and we keep the contours intact. And here is the image on real magnetic resonance imaging for the brain. Okay, so these are, I don't know how much time is left.
I think not much time yet, but if you can.
Yeah, I can wrap up rapidly. Okay, so. Okay. Okay. Also, we applied to construct effective elasticity tensor for polycrystals. Polycrystals are solids made of a collection of bounded grains made of the same crystal. For example, galvanized steel, or here is the quartz, etc. And then if we want to have the elastic tensor, we need to average all the elastic tensor from different orientation. And so if we have a volume average, we take a volume and we take the average, then the effective tensor should be the minimum, the argmin, or the minimizers of this function, with f of q is the orientation distribution function, which gives the texture of the grains. Now, if you the grains are oriented randomly, then we expect the polycrystals to be isotropic. So that's this function, the distribution function is 1. And then if we average using the Euclidean distance, if you average the elasticity tensor, you get something which is different if you average the inverse of the elastic tensors, which is called the compliance tensor. And this is called in the literature Voigt average, and the other one is Wright average. On the other hand, because of the Riemannian metric is invariant under inversion, whether you average using the stiffnesses or the compliances, you get the same answer. So this is one nice thing about Riemannian distance. And also for example, we applied this for cubic crystals, not isotropic. For example, the next things that are low symmetry, high symmetry, is cubic crystal. And if we take the arithmetic average, we get some coefficients of the elastic tensors, which are weighted arithmetic mean with 3/2 to 5th, 3/5 to 5th. If we use the Russ average on the inverse, then we get the harmonic mean with the same weights. And if we take the Riemannian average, then we get the geometric mean with the same weights. So this is a very, very nice property. I think first I thank my collaborators. Yes?
No, it's someone had audio open, so sorry, I muted.
Okay, so I think I finished, and I will be happy to answer any question.
Okay, thank you very much for this wonderful talk. So let's ask to the audience if there are some questions. So as usual, you can use your microphones or write messages in the chat. So please go ahead. Okay, so while the audience is still thinking, So I just have some curiosity. What about the application of these techniques to the inverse problems? So probably inverse problem on the manifold, we can use this kind of techniques. What do you think?
I don't know what kind of inverse problems.
Some kind, I don't know. Just wonder if there are some application to the inverse problems for PDEs, for example. You have mentioned before.
For example, if you inverse problem, you try to use least square in some sense. For example, you have to find the closest operator in some class. So this is if you generalize this with instead of using the Euclidean distance, then you can use Riemannian distance, and then you can define some inverse problem in this sense. But I don't have in mind how for the moment. But it seems to me it is that you can, since inverse problems are usually minimizing least squares,
Okay.
so it could be applied in this sense.
Okay, so thank you very much. I don't know, are there any other questions? Okay, if not, we are a little bit out of time, so I thank you again for being with us, and thank you very much.
Thank you very much. I thank you for this kind of invitation.
Thank you, Anna. Thank you a lot, Professor Maher Moakher, for your amazing talk.